Hello everyone. Once again, welcome to this KTHM e-learning channel. I am SK Marathe and this is my fourth lecture of T.Y.B.Sc Physics Paper First Mathematical Methods in Physics. In this lecture, we are going to discuss topic General Curvilinear Coordinate System. Let us start. General Curvilinear Coordinate System. Then what is Curvilinear Coordinate System? A coordinate system in which the coordinate lines may be curved is curvilinear coordinate system. These coordinates, the coordinates of curvilinear coordinate system may be derived from a set of Cartesian coordinates. We have already derived r theta phi in terms of xyz, rho phi z in terms of xyz. Let us relate the coordinate xyz with three new quantities u1, u2, u3. That is, in this topic, we are going to generalize the coordinate system. In previous lectures, we have studied Cartesian coordinate system, spherical polar coordinate system, and cylindrical coordinate system. Cartesian coordinate system use coordinates xyz. Spherical polar coordinate system use coordinates r theta phi, and cylindrical coordinate system use coordinates rho phi z. The transformation equations are for the general curvilinear coordinate system. We may write the transformation equation like this: that xyz in terms of these new coordinates u1, u2, u3. In the same way as in previous lectures, we have obtained Cartesian coordinate xyz in terms of r theta phi, that xyz in terms of spherical polar coordinates r theta phi, and xyz in terms of cylindrical coordinates rho phi z. In the same way, this xyz in terms of the general coordinates u1, u2, u3. Then the reverse transformation equations, that u1, u2, u3 in terms of xyz. We may write this u1 new coordinates, general coordinate u1, u2, u3 in terms of Cartesian coordinate xy, z. In the same way, as we have obtained in previous lecture, that r theta phi, spherical polar coordinates in terms of Cartesian coordinates xyz, and rho phi z, that is cylindrical coordinate in terms of Cartesian coordinate xyz, that rho phi z function of xyz, r theta phi function of xyz. In the same way, these new coordinates, general coordinate u1, u2, u3 in terms of xy, z. And for each point p in space, for each point having coordinate Cartesian coordinate xyz in space, there is associated set of coordinates u1, u2, u3. In the same way as we have seen in previous lecture, for each point having coordinate xyz, there is a set of coordinates r theta phi in spherical or polar coordinate and rho phi z in cylindrical coordinate. Therefore, for each point P having coordinate xyz, there is a set of new coordinates u1, u2, u3. And to each set, then for each set of u1, u2, u3, there is a definite point in space. These coordinates are called curvilinear coordinates of point P. These coordinates are called curvilinear coordinates of point P. Then through each point P, there pass three surfaces. There pass three surfaces called coordinate surfaces. In previous lecture, we have already seen definition of coordinate surfaces. If one coordinate is held constant, out of three coordinates, if one coordinate is held constant and two coordinates are allowed to vary, then we get a surface. That surface is called coordinate surface. As we have seen in previous lecture, for Cartesian coordinate system, if x is held constant and yz varied, then we get x constant surface. If y is held constant and xz varied, then we get y surface. And if z is held constant, then we get z in Cartesian coordinate. And in cylindrical coordinate, if rho is constant, then we get cylindrical surface. If phi constant, then we get half plane. And if z constant, then we get a plane perpendicular to z axis. In the same way, in general curvilinear coordinate system, if u1 is held constant, u1 is held constant and u2 and u3 allowed to vary, then we get this u1 surface. This surface is u1 surface. This is symbolically shown here, this u1 surface. On this surface, u1 is constant. Then if u2 is held constant, that let it u2 is equal to b. u2 is constant, then we get u2 surface. And if u3 constant, then this u3 surface. That is, on this u3 surface, only u3 coordinate is constant and u1, u2 varies. On each coordinate surface, one coordinate is constant and two are variable. These coordinate surface intersect with each other. These coordinate surface intersect with each other, giving three curves called coordinate curves. In previous lecture, we have already studied definition of coordinate curves, that when two constant surface intersect, then we get a coordinate curve. As we have seen, when x and y intersect, this x surface and y intersect, then we get z line. If y and z intersect, then we get x line. And when x and z intersect, then we get y line. That is, the TU is y line, LM is x line, and EF is z line. Here it is shown. This LM is x line. On this x line, only x coordinate vary. On y line, this TU, y line, y coordinate vary. And on EF, this z line. Along this z line, only z coordinate varies. In cylindrical coordinate, along OP, that is rho curve, rho coordinate vary. On this circle, phi coordinate vary, and along this line, PQ, z coordinate vary. Therefore, this z curve. This way, rho curve, phi curve, and z curve. In same way, in general curvilinear coordinate system, the coordinate curves are u1 curve, u2 curve, and u3 curve. Intersection of u1 and u2, this u1 surface and u2 surface, gives u3 curve. Intersection of u2 and u3, u2 and u3 gives u1 curve. And intersection of u3 and u1 gives u2 curve. Along u1, only u1 coordinate vary. Along u2 curve, only u2 coordinate vary. And along u3 curve, only u3 coordinate vary. On each coordinate curve, one coordinate is variable and two are constant. That is, on u1 curve, u2 and u3 constant. On u2 curve, u1 and u3 constant. And on u3 curve, u1 and u2 constant. Along u3 varies and u1, u2 constant. Therefore, on u1 curve, u1 coordinate varies and u2 and u3 coordinate constant. In this way, this way of seen in Cartesian coordinate, in spherical polar coordinate, in cylindrical coordinate, and then in this general curvilinear coordinates. The coordinate axes of the system are determined. The coordinate axes of the system are determined by drawing tangent to the coordinate curves at a point P. If we draw a tangent to each coordinate curve, if we draw tangent to u1 curve, then we get this first coordinate axis. If you draw tangent, this is a tangent, E2 cap is a tangent to u2 curve, then we get second coordinate axis. And tangent to the third curve, we get third coordinate axis. As we have seen in previous lecture, the tangent to x line, this LM is x line, and tangent to x line gives this I unit vector, that x axis. Tangent to y line gives y axis, and the unit vector along y axis is j cap. and tangent to the z line is z-axis, and unit vector along z-axis is k cap. In cylindrical coordinate, tangent to OP gives E rho. Tangent to phi curve at point P, tangent to phi curve gives E phi curve, and tangent to the z curve, that tangent to this z curve, this tangent Ez cap, this is the third axis. In this way, these three axes at a point P in cylindrical coordinate system. In the same way, in general curvilinear coordinate, tangent to U1 curve gives first axis, tangent to U2 curve gives second axis, and tangent to third curve gives third axis. And if these axes or if these tangents are perpendicular to each other, then the coordinate system is orthogonal coordinate system, that we have to see in next part. Just we have defined curvilinear coordinate. Then let us derive the expression for length element in curvilinear coordinates. We have already seen the position vector in terms of x, y, z by this equation. If this P point having coordinates x, y, z, then with respect to origin, the position vector is given by expression r bar is equal to x I cap plus y j cap plus z k cap. Then the same position vector in terms of the general coordinates u1, u2, u3 may be written like this. That x is function of u1, u2, u3, y is function of u1, u2, u3, z is function of u1, u2, u3. Therefore, r bar is function of u1, u2, u3. Then this r bar position vector in terms of new coordinate, general coordinate u1, u2, u3. The displacement of point P to P dash. If we change the position of point P from this position to this P dash by small displacement dr, then this displacement vector is dr bar. Then position vector for point P is r bar, and for point P dash the position vector is r bar plus dr bar. Then the small displacement dr bar is given by this expression, that dr bar is equal to dabba r bar by dabba u1 into du1 plus dabba r bar by dabba u2 into du2 plus dabba r bar by dabba u3 into du3. This is the displacement along u1 curve, this is the displacement along u2 curve, and this is the displacement along u3 curve. Therefore, the total displacement dr bar is given by this expression. Then in general form, this may be written like this, that I varies from 1 to 3 dabba r bar by dabba ui into dui, that I varies from 1 to 3. Then we get this expression. Let this dabba r bar by dabba u1 may be written by this equation, because unit vector is equal to vector upon magnitude. Therefore, this is the magnitude. Dabba r bar by dabba u1, this is magnitude, and this vector dabba r bar by dabba u1. In the same way, dabba r bar by dabba u2 is equal to this magnitude into unit vector along u2 curve, and this dabba r bar by dabba u3 is equal to magnitude of the displacement into the unit vector along u3 curve. Then this magnitude may be written using new notations, that h1, h2, h3. That h1, h2, h3 are called scale factors. These magnitudes are called scale factors. Therefore, substituting, we get dabba r bar by dabba u1 is equal to h1 e1 cap, dabba r bar by dabba u2 is equal to h2 e2 cap, dabba r bar by dabba u3 is equal to h3 e3 cap. Where this h1, h2, h3 are called scale factors. Scale factors. The scale factors, if for example in spherical polar coordinate, theta and phi are not length coordinates. Therefore, this d theta, d phi, to convert into length, we have to multiply by some factors, and that factors are called scale factors. That we have to see in next part also. This h1, h2, h3 are called scale factors, and this e1 cap, e2 cap, u3 cap are the unit vector along the tangent to the coordinate curves, that is tangent to the u1 curve. E1 cap is tangent to u1 curve, u2 cap, E2 cap is tangent to u2 curve, and E3 cap is tangent to u3 curve. The length element can be expressed as, then the length element, that arc length, can be expressed by this equation, that dl square is equal to dr bar dot dr bar. But just we have seen dr bar is equal to this. Then use two suffixes, that I varies from 1 to 3 and j varies from 1 to 3. Then we get this equation, I summation I is equal to 1 to 3, j is equal to 1 to 3, dabba r bar by dabba ui into dabba r bar by dabba uj into dui into duj. Let use another notation for this product term, that gij. This gij, the gij is called metric coefficient, that we have to see in the next part. This metric coefficient gij is equal to dabba r bar by dabba ui into dabba r bar by dabba uj. I varies from 1 to 3 and j varies from 1 to 3. Therefore, we get 9 values of gij. When I varies from 1 to 3, j varies from 1 to 3. Therefore, we get 9 product terms. That 9 product terms are these. I is 1, j is 1, I is 1, j is 2, I is 1, j is 3, then I2, j1, I2, j2, I3, j3, I3, j1, I3, j2, and I3, j3. In this way, we get these 9 terms or 9 metric coefficient terms. Substituting these 9 metric coefficient terms, the length element may be written like this: dl square is equal to g11 du1 square, g12 du2 du1 into du2, g13 du1 du3, like this. In this way, substituting these 9 terms, the arc length is written by this expression. In general form, this length element dl square is equal to this gij into dui into duj. The gij may be written in matrix form, therefore it is called metric coefficient. This is the expression for length element. This is the expression for length element in general curvilinear coordinate. The term gij is called metric coefficient. Let us derive the expression for length element in orthogonal coordinate system. Then what is orthogonal coordinate system? When the tangent to the coordinate curves are mutually perpendicular. The tangent to the coordinate curves are the coordinate axes. If the coordinate axes are mutually perpendicular to each other, then that coordinate system is called orthogonal coordinate system. As shown in this figure, tangent to u1 curve is e1, tangent to u2 curve is this e2, and tangent to u3 curve is e3. E1, E2, E3 are mutually perpendicular to each other. Therefore, this system is orthogonal coordinate system. Then for orthogonal coordinate system, the product of the unit vectors, the dot product of unit vector with itself is equal to 1. When we take dot product of unit vector with itself, then dot product is its magnitude into cosine of the angle, cos of the angle. The angle is 0 and cos 0 is equal to 1. Therefore, E1 dot E1 is equal to E2 dot E2 is equal to E3 dot E3 is equal to 1. And the dot product of perpendicular vector, E1 is perpendicular to E2. When vector perpendicular, angle 90 and cos 90 0. Therefore, E1 dot E2 is equal to 0, E2 dot E3 is equal to 0, E3 dot E1 is equal to 0. And cross product of two vector. For cross product, a bar cross b bar is equal to ab sin theta. Sin theta. When we take cross product with itself, theta 0, sin 0, 0. Therefore, the cross product of vector with itself is equal to 0. And according to right hand rule, this cross product of E1 cross E2 is equal to E3, E2 cross E3 is equal to E1, and E3 cross E1 is equal to E2. If we take in clockwise direction, then this E1 cross E3 is equal to minus E2, E3 cross E2 is equal to minus E1 and E2 cross E1 is equal to minus E3. Applying these rules in this equation, for this 9 equation, where I is not equal to j, then these terms are perpendicular. This is dabba r bar by dabba u1 is perpendicular to dabba r bar by dabba u2. Therefore, value of g12 is 0. In the same way, dabba r bar by dabba u1 is perpendicular to dabba r bar by dabba u3. Therefore, g13 is equal to 0. g12 is equal to 0. g13 is equal to 0. g21 is equal to 0. g23 is equal to 0. g31 is equal to 0. g32 is equal to 0 because this perpendicular to each other. Therefore, only 3 terms remains, that is G11, G11, G22 and G33. Therefore, out of these 9 terms, only 3 terms remains, and we get, thus for orthogonal curvilinear coordinate system, the metric coefficient Gij is equal to 0 for I is not equal to j. Therefore, dl square is equal to, only these 3 terms remain, g11 du1 square, g22 du2 square plus g33 du3 square, or dl square is equal to dl1 square. Substitute g11 du1 square is equal to dl1 square, g22 du2 square is equal to dl2 square, g33 du3 square is equal to dl3 square. Then this is the expression for length element in orthogonal coordinate system. Dl square is equal to dl1 square plus dl2 square plus dl3 square. The scale factors and metric coefficient are related with each other. The scale factor h1, h2, h3 and the metric coefficient g11, g22, g33 are related by this equation. h1 is equal to square root of g11, h2 is equal to square root of g22 and h3 is equal to square root of g33. Therefore, hence dl1 is equal to h1 du1, that length element, magnitude of length element along u1 is dl1 is equal to h1 du1, along u2 dl2 is equal to h2 du2, and along u3 is dl3 is equal to h3 du3. This is the scale factors and the length element in orthogonal curvilinear coordinate system. That's all in this lecture. In next lecture, we will derive this length element, volume element, area element for Cartesian coordinate system, spherical polar coordinate system and cylindrical coordinate system, and for general curvilinear coordinate system.